Hi, I'm Will Sutton.
And I'm Daniel Grubb. And our presentation begins with a review of scatter plots and the analysis of them, including the least-squares regression line and the variables that go along with it.
We follow this discussion of the LSRL with an introduction into re-expression of data, both how to do it and how it applies to real-world data that is not linear.
So this is a scatter plot. A scatter plot is a graph that's used to display two sets of data. So on a scatter plot, for the x-axis you have the explanatory variable, and for the y-value you have the response variable. So the response variable is how the second set of data sort of reacts with the explanatory variable, which is inputted. So when talking about a scatter plot and the relationship between the two sets of data, we can use two words, association and correlation. So association just means the relationship if there's a pattern that shows between the two sets of data, where correlation is the same sort of thing, but if the data is more linear. So the correlation is more the linearity of the data, whereas association is just if there's a relationship in general. We are able to predict how a scatter plot will behave using a least-squares regression line, or an LSRL.
Recall from your earliest days in mathematics that when you have a series of points, you can draw a line of best fit that tries to describe the data in a linear sense. So the LSRL is a mathematically defined version of this old school line of best fit, given by the form y hat equals b sub naught plus b sub 1 times x, when b sub naught is our constant, b sub 1 is our slope, and x is our input or explanatory variable. The output of this is the predicted response, which allows us to determine what, if the line is, or if the graph represents a good linear model, what, as our explanatory variable changes, what the graph will produce. There are several other variables aside from b sub 1 and b sub naught that allow us to determine how good of a fit the LSRL is to a given scatter plot. Using any sort of calculation utility that can provide linear regression statistics, you will get two particularly important values: r, the correlation coefficient, and r squared, which is a loose term for the percent of variation that is accounted for. R determines how good of fit the LSRL is to a given scatter plot. This is a number between 0 and 1, and the closer to 1 it is, the more overall linearity that the scatter plot possesses. Conversely, a low R means that the scatter plot is hardly linear at all, and in some cases this may lead to re-expression, which is something we will cover later. R squared, as said here, is the percent variation accountability number. And R squared basically tells us how much of the variation in the y variable, or the response variable, is due to variation in the x variable, or the explanatory. What this allows us to do is not only look at the LSRL as a tool of analysis, but also determine overall if our sample is representative and how good our data is at expressing the relationship between the two data. We can use R squared to examine the differences between data and perhaps infer several things about what may cause differences between outputs. Here we have an example of a scatter plot and its corresponding least-squares regression line that displays a strong linear correlation, as well as a strong relationship between the explanatory variables and the response variables. Its R value, negative 0.9623, indicates that it has an incredibly strong linear correlation in the negative direction, hence the negative. It's important to note that the proximity of the absolute value of R to 1 dictates how strong the linear relationship is. Also of note is the R square value of 92.6%. What this indicates is that 92.6% of the variation in these variables on the response axis is due to variation in the x-axis, which indicates that this data has a very strong influence on that data. Conversely, here is an example of a scatter plot and corresponding LSRL that does not display a strong linear correlation. As you can see, the data are rather sporadic, and our R value of negative 0.2038 indicates that there is almost no linear correlation between these data. Correspondingly, the R squared value of 4.15%, indicating that only this much of the variation in the response is due to the variation in the explanatory variable, indicates that these data may not have much relation to one another. However, in other examples, you may see that a linear relationship does not exist, but there could be a clear pattern to the scatter plot. Through examining what is known as the residual between a datum and its predicted value on the LSRL, we can examine whether or not there is an association that may not be linear between data points.
So residuals are the distance of points on the scatter plot from the point to the LSRL. Now to find these residuals, you can use the equation E, which is the residual, or the error, equals the actual y value from your data minus the predicted value from your LSRL equation. So to graph a residuals plot, you use the residuals as the y-axis, or the response variable, and the x values for the explanatory variable. Now, when you're looking at a residuals plot, what you want to see to check if your LSRL is an appropriate fit is the shape of the plot. So if it's just a boring, just standard, just points everywhere, then that suggests that the model is a good fit if there is no pattern to the points of the residuals. Now, if there is a pattern, this suggests that the linear model is not a good fit.
So what do we do if our LSRL does not accurately predict the output of a scatter plot? Say we have a set of data that have a clear association that's exponential, or perhaps looks like a square root. Our linear model cannot accurately predict what's going to come of that. But there is still a way for us to figure out what may come from extrapolated data, and the answer is through re-expression of scatter.
Now, re-expression is a tool that we can use to predict outputs for a set of data that is non-linear, even if it might have a strong association. Now, this is significant because data is often not linear, but by being able to just change it a little bit and tweak it around, we're able to re-express it and predict much more accurately. Now, when re-expressing data, you use a series of different tools. And this series of different tools is called the ladder of powers. Now, when you're using the ladder of powers, you apply function operations to the data. Now, this can include squaring the data, square rooting the data, logging the data, using the opposite reciprocal, and even using the square root of the opposite reciprocal.
And now it is time for a calculus connection. Recall from pre-calculus that inputting an inverse function into a function, or vice versa, yields x for all possible values of x. The graph of the function y equals x is linear, and it is this connection that allows us to intuitively determine which type of re-expression to choose. It's based on inverses. So, several functions have known inverses, and you can detect those functions by shape. For example, a clearly exponential function can be linearized if you use its inverse, the logarithmic function. If you have something that resembles an exponential growth in terms of data and scatterplot arrangement, you can log the data or take the natural log of the data in order to linearize it. The same applies to square roots and negative inverses. Now, all of our work aside, if we want to actually make sense of our predictions, we are going to have to convert out of our addled function. And we can do that again through using inverses. We do this because you have to have consistent units. Say you're trying to measure how much money it's going to cost to do something. You can't measure that, well, you could, it's just illogical. You can't measure in terms of square root dollars or 1 over the negative square root of coins that it will cost you. It just doesn't work. So, to illustrate this concept, we're going to use a fitting monetary example. So say you live in Somalia. You need to feed your family. You would like to buy a bag of rice, but you're not sure how much it's going to cost you. So you pull your friends, you pull your enemies, you pull everybody. And you construct a scatter plot. And you find out that the relationship between the weight of the bag of rice and the money that it costs to buy it in Somali shillings is exponential. You can't predict that linearly. It's illogical. So instead you re-express, and we are given the re-expressed LSRL equation. The natural log of the predicted cost is equal to 6 plus 1.53 times the size in pounds. Now let's say you want to buy a 10-pound bag. We're going to insert this into this equation. So we're going to have natural log of c predicted is equivalent to 6 plus 15.3, because that is equivalent to 1.53 times 10. Adding this together, you get 21.3 is equivalent to the natural log of the predicted cost. How do we get out of this? It's simple. Remember how our original graph had an exponential tendency, and we took the natural log in order to get out of it? We're going to do the exact same thing backwards, and we're going to raise everything to the, or we're going to e everything. E to the ln c hat is going to just be c hat. And we're going to have e to the 21.3, which is equivalent to predicted cost of 1,780,215,035 Somali shillings. I did that in my head. Now, we can see here that we are now given a predicted value in terms of a real-world unit, the Somali shilling. And you also notice that this actually makes quite a lot of sense given the value of the Somali shilling. Were we to not re-express or not evaluate out in terms of exponents, we would be left with natural log of Somali shillings. Easy enough to get out of, but it doesn't make sense. I would not walk up to the storekeeper and say, I have exactly this many natural logs of Somali shillings. Anyway, this is a relatively applicable example of how you can use inverses in order to get yourself back out of re-expression of LSRL equations.
Now, you can re-express data fairly easily and quickly using a calculator. So, if you take your explanatory values and you put them into list 1, and then you take your response variable values, the corresponding ones to these values, and insert them into list 2, then you can re-express the data quite simply and easily. All you have to do is take the square root, or whatever re-expressing tool you're using, of list 2 and store it into list 3. Then, when you're generating your LSRL, you just use the list 1 for your explanatory values and list 3 as the re-expressed, and you use them as your response variable values. Now, let's look at a more complete example of re-expressing data using a calculator. So, here is a scatter plot of the length of fishing line versus the poundage that it will hold, with the poundage, the strength, as the x, or the explanatory variable, and the length of the line as the response variable. So, as you can see, it is not linear, and using a linear model here would be most illogical. So, to re-express it, what we're going to do is we're going to take the negative reciprocal of list 2 and store it in list 3. Then if we ran it here, if we ran it again, here is the new scatter plot re-expressed. As you can see, it is much more linear, and a linear model would be much more appropriate. Now, using this more appropriate model, if, say, we wanted to find the length of fishing line that would hold 200 pounds, then we would just use this equation. So what we would do would be, we would insert 200 pounds for x, or s in this case, so -1 over length hat equals -0.023 minus 0.000373 times 200. Then, -1 over, we'll call it length hat, equals -0.0976. So, we're not quite done yet, because we're still in these units, so we have to convert it back. So, multiplying length over and dividing by -0.0976, we get length hat equals 10.2459 yards. So, you can see how we used the more appropriate model to find the value and then we converted it back and got our value in yards.
So, where does this all fit together in the grand scheme of things? What am I ever going to do with knowledge of regression and re-expression? Well, it's simple. In any work that involves statistics, you need to be able to extrapolate data. You're never going to be able to perform an infinite sample of infinite size. You're not going to be able to census everything. So we build models. It's the way that all of our sciences work. And linear regression analysis allows us to model relatively linear models, and thus re-expression allows us to extend that model to things that don't fit the linear pattern. So whenever you've got a sample and you need to extrapolate beyond what your sample allowed you to observe, you can simply use a regression model and then the tests which we've discussed in the past in order to determine whether or not it is a solid fit. And if it is a solid fit, then you can use that model to extrapolate further from your sample. In conclusion, this is a topic that has a wide range of applications throughout statistics, but also in the sciences and in other branches of mathematics that have to do with dealing with information. So, I hope that next time you are gathering data on random groups of people that you remember to always use the linear. Thank you.